This is the video for the second half of the note-taking that deals with independent and dependent events. So picking up with our discussion, we've got to draw the card from a standard deck of cards, replace it, and then draw a second card. Okay, so this is our experiment. We're going to draw a card, replace it, and then draw a second card. What is the probability of drawing a queen and an ace? Okay, so when we see that word "and" in the problem, we're thinking, oh, okay, when I see "and," that's a product, that's a multiplication. So the probability of drawing a queen and an ace, probability of drawing a queen times the probability of drawing an ace. Now, are these two events independent events? Why, yes, they are, because you can, when you draw a queen and then you replace it back in the deck, you still have the same number of cards in the deck to draw from for the ace. So the probability of drawing an ace on the second draw is not affected by drawing a queen on the first draw. So we're going to take and multiply these two together. So the probability of drawing a queen out of a standard deck of cards, there are 4 queens out of 52 cards, and we're going to multiply that times the probability of drawing an ace, and there are 4 aces out of 52 cards, and our product simplified is going to end up being 1 over 169. So that's our probability, 1 over 169. Another type of situation to consider is, suppose we draw 2 cards from a standard deck of cards without replacement. Now, notice the difference here. We're going to draw a card, keep it out, and draw a second card. The question here is, what's the probability of drawing an ace and a king? So I'm looking at the probability of drawing an ace on the first card, but when I get ready to draw my second card, things have changed. I no longer have 52 cards in the deck. I only have 51. And I no longer have 4 aces, I only have 3. So I'm going to say, since this second one is being affected by the first, this is going to be the probability of drawing a king given that the ace was drawn. Okay? So the probability of drawing an ace, there are 4 aces in the deck out of 52 cards, times the probability of drawing a king given that an ace has been drawn. Okay, so how many kings are in the deck? There are 4. But now, how many cards are in the deck because we took out an ace? 51. So now we're going to multiply these, and our final answer reduced is 4 over 663. Okay, so notice the difference with these two problems. The first one deals with independence. This first problem, the two are independent events. This one is a problem that deals with dependent events. Okay, so looking at one that's in your textbook, we have here at a university in western Pennsylvania, there were 5 burglaries reported in 2003, 16 in 2004, 32 in 2005. If a researcher wishes to select at random 2 burglaries to further investigate, find the probability that both burglaries will have occurred in 2004. Okay, so now with this one, we want the probability that both will have occurred in 2004. So we're looking at the probability of crime 1 and crime 2. Okay, now before I start solving this problem, I really need to think, are these events independent or dependent? And notice here they've classified them as dependent because we're looking at events that occurred in 2004, 2 crimes that occurred in that year. So if I say the probability of the first crime, because there are 16 crimes in 2004, and there's a total of 53, when I go back and add the 5 and the 32, I get a total of 53. That's the probability that a crime was committed in 2004. But that both of them means that the probability of the second crime given the first has occurred. So given that we've had a crime already committed in 2004, what's the probability the second one was committed in 2004? So notice here that it reduces the numerator by 1 and the denominator by 1, because we only now have 15 crimes because we accounted for one with the first probability, and we only have 52 crimes total, okay, because these events were dependent. So we're multiplying these two probabilities together to get our answer of 60 over 689. Okay. Now, when something happens like that, and we're considering the probability of an event given that something else has occurred, the first event has occurred, we're looking at what's called conditional probability. Conditional probability is the probability that the second event B occurs given that the first event A has occurred. And this is our rule for conditional probability, so we definitely want to add this to our notes. This rule for conditional probability. Looking at example 433 from your text, it says the probability that Sam parks in a no parking zone and gets a parking ticket is 0.06. And the probability that Sam cannot find a legal parking space and has to park in the no parking zone is 0.20. On Tuesday, Sam arrives at school and has to park in a no parking zone. Find the probability that he will get a parking ticket. Okay, so now this is what's happened. He had to park in a no parking zone, so we want to know what's the probability that he will get a parking ticket given that he parked in the no parking zone. So look at how that's set up. Probability of a ticket given that he parked in the no parking zone. Now, to solve this problem, we go back and use our formula. Our numerator is the probability of N and T. This is where we're going to have to be very careful in reading these problems, because up here at the very beginning it tells us the probability that he parks in no parking and gets a parking ticket. So it's telling us that and statement. And gets a parking ticket is this number, 0.06. So that's our numerator. The probability that he parks in a no parking zone, that's going to be the 0.20. And we're just going to plug into the formula and simplify to get 0.30. Another example of conditional probability. Here we have a chart. We've got a recent survey asked 100 people if they thought women in the armed forces should be permitted to participate in combat. The results of the survey are shown. Okay, so this is our information that we're given to work with. Well, the first question is, find the probability that the respondent answered yes, given the respondent was a female. So now look at this now. We're looking for the probability that they answered yes, given that the respondent was a female. So this is the way our setup is. Probability of yes given a female. So now we're going to go back and look at our information in the chart. The probability that they answered yes given female, first of all we have to consider this and statement. Female and answered yes. So we're looking at female, yes, and notice where they intersect here at 8. So that's 8 out of 100 total. This is the total number. And then the probability that they're a female, well, we're going to just read across the female row. That total number is 50. So we got 50 out of 100. And then we're going to reduce that to 4/25. Now, another way of looking at that particular problem is we could have been asked probability that they answered yes given that the respondent was a female. Just consider this. Just consider the female part, because that's what we're given. Okay, if I do that and I want to know what's the probability that they answered yes, notice that there are 8 yeses out of the females of 50. And 8 over 50 reduces to our answer of 4/25. So we could do it that way as well. I just wanted you to be aware of that. The second part of that same problem asks, what is the probability that the respondent was a male given that the respondent answered no? Be careful with the order. Male, given, answered no. Okay, so notice how it's set up. Probability of male, given that they answered no. So here again, we're looking at the and statement for our numerator. Male and no. So go male, no, and that's 18. 18 out of 100. And the probability that they answered no. So we look down the whole row for no, and that's 60 out of 100. And that reduces to 3/10. The last type of problem I want to look at with you is example 437. This one deals with a situation where you're considering the words at least in the problem. This one says the Knitwear Association of America reported that 3% of ties sold in the United States are bow ties. If 4 customers who purchased a tie are randomly selected, find the probability that at least one purchased a bow tie. Now, to find out the probability that at least one purchased the bow tie means that you could have 1 purchase it, or 2 people purchased a bow tie, or 3 people purchased a bow tie, or 4 people purchased a bow tie. So really you're looking for all those. 1, 2, 3, 4. That's kind of hard to find. So what we're going to do is we're going to look for the probability that there were no bow ties purchased, and then once we find that, we're going to take that answer and subtract it from 1. Okay, so that's our goal. We're going to get to that point. So to do that, let's go back to what we do know about probabilities. We're given the probability that they purchased the bow tie is 3%. So remember what this is right here? B bar, that stands for complement. So the probability that they do not purchase a bow tie is going to be 97%. So for 4 people to not purchase a bow tie is going to be 97% times 97% times 97% times 97%. So what are we assuming about these events? These 4 people purchased bow ties. Are we assuming that they're independent or dependent? Yes, that's right. We're assuming that they're independent events. And we get this product of 0.885. So now to find at least one bow tie, we're going to take 1, subtract the probability of no bow ties, and that gives us our final answer. So we needed the complement of this, the complement of the 0.885. I hope this helps with your homework, and look forward to seeing you again on Thursday night.